Hey guys, this is just going to be a video going over the solution set for the practice exam that I gave out in Thursday's class. We did a practice exam in class, hopefully that helped, but this is for the take-home practice exam that I gave you guys that says no need to turn this in on the cover. You know, the way that I'd recommend you go through this video is that you first try the practice exam to the best of your ability, and then give yourself an honest assessment on each question to see if you're really ready to take that in an exam situation or not. You know, if you weren't able to finish one of the problems, that means you got to study it. If you weren't even able to start one of the problems, that means you got to study it a lot. So yeah, I would recommend you trying to do this whole exam before you watch this video. So that's probably the way that I would do it, but you guys are free people and you can study whatever way you want. Okay, so for problem number one, I've said factor this guy completely. So the first thing we do whenever we're asked to factor something completely is we look for a common factor that we can pull out of every single term. Well, if you take a look at this, you will see that the coefficients don't have a common factor, but there is a common factor of x in each term. So I'm going to go ahead and pull x out and then see if there's anything else to do after that. So I pull my x out. That leaves me with 2y to the fourth plus 3x squared minus 1. Okay, so now what I want to do is take a look at this inner polynomial and say, can I factor this at all? So when you're sitting there on the exam, if you want to say, well, can I factor this, and you don't know if you can or not, sort of write out what the factors would look like if it could be factored. Right, and so my initial term is y to the fourth, 2 times y to the fourth, right? And so this would split up as 2y squared and then a single y squared. And now we got to kind of think about, if we could fill in this area, what would we fill it in with? Well, if we filled it in with, let's say, just plain numbers, let's say plus 1 minus 1, there's no way to get the x term out of that. If we put an x term over here, let's say we said plus 1x, then we would have some term, we'd have probably 2 terms actually, that actually had an x and a y in it. But that's not the case in our inner polynomial here. So we really can't make a polynomial like this. You know, something that might be factorable if it had all these x's and y's in it would be something like 2y to the fourth plus 3xy plus, you know, I don't know, 9x to the fourth or something like that. Now that one, that would be worth doing a whole brute force or doing factor by grouping to kind of figure out what's going on with it. And that's because we have this middle term with the x's and the y's, and so, and actually these would be squared, I think, in this case. So it's kind of like, yeah, you have to kind of think about how is it possible to make this combination. And with the one that we just went over, no, it's not possible. So this would be our final solution. I know that one's a little bit disappointing because all we did was factor out the x, but sometimes that's all you can do. All right, next one. So here is a basic factoring problem. When we have a factoring problem where it is a second degree, we know that we need to split it up into 2 binomials. There's no single factor that we can take out of each and every term, so we just go right about factoring this guy. I know that it's going to break up into 2 binomials with x as the first term because of this first term right here. Now, I'm going to take a look at my last term, which is a negative 10. The only way to multiply 2 numbers and get a negative is to have a positive and a negative. So I'm looking for 2 numbers, p and q, such that p times q equals a negative 10, and p plus q is equal to a negative 3. Well, I'll just go ahead and make the table, although you guys should be used to this by now. So on this side, I'm going to put pair factors of negative 10, and I want sums of negative 3. So pair factors of negative 10 that sum to negative 3. I only attach the negative to the larger factor because this is a negative number right here. So negative 10 and positive 1. When those multiply together, I get negative 10, but the difference is negative 9. So that's not two factors that I wanted. Well, since we're talking about 10, there's only two other factors that we can consider. Negative 5 and a positive 2. And when we take 2 minus 5, we do in fact get a negative 3, just like we wanted. So those are the factors. Minus 5, positive 2. And remember, this is kind of like the this example that we just did here. This is sort of like the easy example of the table when we don't have a coefficient out here in front of the x. Remember, when the coefficient's out in front of the x, and we kind of do this game where we multiply the first and the last terms in the polynomial, that one's a little bit different, right? We do things a little bit different in that. After we create our table in that one, we actually rewrite our initial polynomial. In this one, we just plug our factors right into the polynomial. This is our final answer. Okay, so here is one of those problems where we have a coefficient out front, the 6 right here. That's going to give us a lot of troubles if we're not careful with it. So one method is the brute force, and that method means that you literally write out all the possibilities, right? You'd have like 6x and then a plain old x. That would be one possibility. 2x and a 3x. That would be another possibility. And that's it. That's all the possibilities. And then you'd have to check these, right? Since negative 1 is the last term, you'd have to check these with plus or minus 1 in each side. And you'd have to figure out which one works. That's your brute force method. Uh-oh, I gotta fall. Okay, where was I? I was just explaining how the brute force method is a big pain in the rear end. The best method when it comes to these guys with coefficients out front is where we multiply the first term by the last term and then find the sum which adds to the middle term. So I'm going to create another table. I'm going to say first term times the last term. That gives me a negative 6. And I'm looking for factors of negative 6 that sum to negative 1, or differ by negative 1. Differ by 1, I should say. So let's see now. If I want factors of 6 that sum to negative 1 or differ by exactly 1, 6 and 1 clearly aren't going to cut it, right? Because 6 and 1 differ by 5. So the only other two factors that I'm looking at are 2 and 3. If I'm looking for a sum of negative 1, then I want to put the negative on the 3. Negative 3 times 2, negative 3 plus 2 equals negative 1, and we have a winner. Now here's the next step, right? And this is the one that sometimes we forget, and we confuse these problems with the last one where it's easy. This is not too difficult, but we just have to remember this one step where we split up this middle term. So the first term comes straight down. We get a 6x squared. But the negative x actually turns into a negative 3x and a positive 2x. And then the negative 1 still comes right down. And so these are still equal to a negative x. We've just grouped them in a convenient way. Speaking of grouping, this is where we do our grouping step. So what can I pull out of these first two terms? Well, I can definitely pull a 3 out. It also looks like I can pull an x out. So I'm going to pull out 3x, and that's going to leave me with 2x minus 1. All right, and then I'm going to notice that the other one, I can't pull anything out, but that doesn't really matter, whoops, because I have exactly the factor that I wanted. So now I have my matching binomials here, which means I'm allowed to do my factoring by grouping. So now I'm going to pull the 2x minus 1 out, and I'm going to write what's left. 3x from up here, and then from right here, we have a +1. Don't forget that +1. That's crucial. If you forget this +1 out here, man, oh, I'm going to be so disappointed. Just kidding. I'll probably just laugh a little bit. So anyway, this is our final answer here. If I want to check this answer, I go ahead and FOIL it out, and I make sure that it actually equals the polynomial that I was originally breaking down. All right, onward. So now that we've gone over how to factor stuff, now that we've learned how to factor stuff, or not learned, I guess we've reviewed how to factor stuff, let's go into how to use factoring to solve an equation. Remember, to solve any equation that's more than a degree 1, right, if our equation looks like this, x minus 5 equals 0, we don't need to factor anything to solve this. We just need to isolate x. But if it looks like this, x squared minus 4 equals 0, then we have to factor stuff. We can't just add 4 to both sides and then assume things are going to work out. We've got to factor. So let's try that out. Let's do one of these problems. I mean, basically, the hardest part of any of these problems is just to factor the polynomial. So I'm going to notice that I don't have a coefficient in front of my x, right? And that means this is one of those easy examples where it just breaks down into two binomials, right? So we have x, and that equals 0. So now what we're looking for, we have a positive 21 here, which means that the signs in the middle have to either be both positive or both negative. Since we have a negative for the middle term, we know that these both have to be negative. So what two terms, when multiplied, equal 21, and when added, equal 10? 21 and 1 clearly doesn't work. Our only other options are 7 and 3. All right, so now the final step of this is I need to take each of these factors and say what values of x would cause that factor to be 0. So for this first factor, x minus 7, if x were equal to a positive 7, then we'd have 0, and the whole equation would be true. So x equals 7 is a solution. Now this factor, if x were equal to a positive 3, then the whole equation would be 0 again, everything would be true, and everything would be, lollipops and rainbows. So these are the two solutions to this problem. Now remember, this isn't a rational equation, so there's no restrictions, so we don't need to check these solutions to make sure if they actually exist or not. That'll kind of hold off until the rational equations part. But for these ones, any solution you get is just a solution. Unless it's a word problem, then those solutions have to make sense in order to be solutions. All right, aha, the classic evaluate problem. Near the beginning of this class, and I'm looking for my calculator right now, there it is. Near the beginning of this class, I told you that evaluation problems would be on every single test. And I am not wrong about that. Here's another evaluation problem. You're going to see one on the exam, no doubt. Evaluation problems are very basic. They just give you a function that typically looks confusing, like this one, and then they give you a value to plug into that function. All you need to do to complete this problem is plug in the value and calculate. So this problem is the height. This is about wave height. This says the height of waves in a storm depends on the speed of the wind. Assuming the wind has no obstructions for a long distance, the maximum wave height h for a wind speed x can be approximated by this polynomial. And so h over here is the wave height. X over here in the body of the polynomial, that is the wind speed. The question says, what would be the wave height if the wind speed were 10 knots? Okay, so to do that, we just say h, that's what we're solving for, equals 0.03 x squared 10 squared, right? We plug it right in and we leave our parentheses there, plus 0.6 times 10 minus 6. So I actually didn't need a calculator for this particular part because when we multiply by 10, 2 powers of 10, this is really multiplying by 100, right? And, well, maybe I'll just do this so you can see the middle step. But I don't need this middle step. I can already see what it's going to be. This is 0.03 times 100 plus 0.6 times 10, again, minus 6. Now remember, when I multiply by 100, that's the same as moving this decimal place 2 places over to the right. So this 0.03 turns into a plain old 3. The 0.6 turns into a plain old 6, and the minus 6 stays the same. These guys cancel out, and I get h equals 3. So you would say when the wind is 10 knots, the wave height is 3 feet, or some formulation of that sentence. All right, so there we go. Remember, evaluation problems. If ever I give you a problem that says evaluate, that's a plug-and-play problem. You plug in the number, you calculate, and you're done. All right, evaluation problems. Those are definitely like the easiest points that you can get on any exam. Okay. Here's a problem where we are asked to divide two rational expressions. So just remember, when you're asked to divide two rational expressions or divide two fractions, you just need to multiply by the reciprocal of the divisor. So on this very next step, I'm just going to rewrite the numerator here, 3x plus 10. And then I'm going to flip this fraction over here. Now I multiply straight across. So I have x minus 1, x plus 2, over 3x plus 10 times 2x minus 1. Now, let's see if we can factor anything out to maybe simplify this. You really can't, right? 3 and 10 don't have a common factor. You know, these are all prime already, and so is this one. Everything's prime. So basically, that's the end of the problem. That's all you needed to do for a full 10 points on this problem. You should keep that in mind that sometimes I make these problems myself, so sometimes they don't turn out quite like you might expect the problems in the book to turn out, right? Like if you did this in the book, you'd expect at least one of these to cancel. But they didn't. They just can't. And so that's it. That's the full 10 points right there. All you needed to do was flip one rational expression over and multiply it. So, onward. All right, here is one of those complex rational expressions. So we're going to go over both methods on how to complete this, okay? So let's do method 1 first. Method 1. Method 1 is the one where you treat the numerator and the denominator sort of separately and combine those fractions, and then you have a plain old rational expression which you can flip and multiply. So here's method 1. So I have 1 plus x over y over 1 minus y over x. So I'm going to go ahead and handle the numerator first. In order to add the fractions in the numerator, I need to have a common denominator of a y. So I'm going to multiply my, So I'm going to multiply that first term, 1, which is actually 1 over 1, by y over y. I'm going to add that to x over y. All right, now I'm going to go ahead and do some work in the denominator. So I have my 1 over 1, and now I need x in the denominator, so I want to multiply this by x over x. Y over x. There we go. All right, now I'm going to go ahead and just combine these fractions. I have y plus x over y. And then I have x minus y over x. All right, and so now we're in that last step where things are easy, and all we need to do is flip this lower rational expression and multiply by the upper one. So let's go ahead and do that. I have y plus x over y, and that's multiplied by x over x minus y. Okay. And that's it, right? There's nothing else that I can simplify here. I just have x times y plus x, and then I have y times x minus y. Yeah, I mean, I'd be tempted to pull out a negative, but that doesn't really work because there's no negative term up here, right? If this term up here were y minus x, then I have something. But it's not, so I really don't have anything. And as you guys can see, sometimes the problems I make are very unsatisfying. Okay, so let's try method 2. What would this look like under method 2? So on method 2, we would just recognize, oops, okay, so 1 over x over y. All right, so I just recognize that I have only two denominators. They're both prime of sorts. So my common denominator, my LCD, is going to be yx. So I'm going to multiply top and bottom of this complex rational by yx. All right, so this, when I distribute in here, I get yx plus, when I distribute into the second term, the y's will cancel and I'll get x squared. And then on the bottom, when I distribute in, I once again get yx. And when I distribute into the second term, the x's will cancel and I'll get minus y squared. Then, of course, when you factor everything out, you factor out a common x, you get y plus x. And when you factor out a common y, you get x minus y. And there we go. We're in the same spot that we were up above. You can't really simplify this any further, even though I wish I would have written this problem better, because that would be a little more fun. But what are you going to do? We can't all win the lottery every day. Okay. Here we go. Here is another example of a rational equation. So remember, this is an equation, which means that we get to handle this a little bit differently than we did in the last problem, right? The last problem wasn't an equation, so we couldn't multiply everything through by a single number, right? In the last problem, we had to multiply top and bottom by yx, which is essentially just multiplying top and bottom by the number 1. Sorry, multiplying the whole fraction by the number 1. In this one, we multiply through every term by our LCD. So it's similar in some ways, but different in other ways. Okay, so my LCD is clearly, in this case, x minus 1 and x minus 2. And that's because this factor, or this number, or whatever, this set of factors contains all the other factors in it. So I'm going to multiply every term by that. Uh-oh. Just pretend that I wrote this over here, so we're multiplying it in. And just pretend that this is really pretty handwriting. Okay, so I'm going to erase my LCD so I can give myself a bunch more room here, because I'm going to need it for this one. So I'm going to go ahead and write this out sort of the long way, right? And so when I multiply x minus 1, x minus 2 into this very first term, I get x minus 1, x minus 2 over x minus 1. When I multiply it into this second term, this guy over here, I get x times x minus 1 and x minus 2. And that's all over x minus 2. That is equal to 2 times x minus 1, x minus 2, all over x minus 1, x minus 2. Okay. Now I go through and I cancel my like terms here. Boom, boom, that cancels. Boom, boom, that cancels. Boom, 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 boom. Those all cancel. Haha. I like that one. Okay, so now I write what I have left. I have x minus 2 from this factor here. Then I have plus x times x minus 1 from this factor here. And then that is equal to a plain old 2, which is what I got when I canceled all those factors from on the right side. So now I go ahead and I want to distribute everything. I want to basically create a problem that I can solve here, right? So I got to distribute this guy. So I have x minus 2 plus x squared minus x equals 2. I do have a squared term, which means I need to consolidate everything on one side, set it equal to 0, and then factor it out. So clearly right here, it looks like I have opposites on my x's. X minus x equals 0. Then I have x squared minus 2 equals 2. If I subtract 2 from both sides, then I have x squared minus 4 equals 0. And then I go ahead and factor this guy out to figure out what my possible solutions are. So I have x minus 2 and x plus 2. Right? And that was so easy because this is a difference of squares. Right? A squared minus b squared. Memorize those difference of squares. They're going to save you a lot of time. So now I solve each factor. Right? I say, what would make this factor 0? Well, x equals positive 2 would do that. What would make this factor 0? X equals negative 2 would do that. So now I recall that this was a rational expression, right? And so that means that I should have, right off the bat, restricted values. Like a dork, I did not, because that's just how I roll. So here, I'm going to erase all this junk around it, and we're going to go ahead and restrict our values up here. So remember, we restrict any values that might render these denominators 0. The only two numbers that are going to do that are, if x equals a positive 2, a denominator will be 0, and the whole thing is undefined. So I'm going to say x cannot equal positive 2. And over here, I'm going to say x cannot equal a positive 1, because that's the same situation. Now I go back down to my solutions. Aha. So I have a restriction that x cannot equal, right? But x cannot equal a positive 2. So this is not a solution, which means this is my only solution for this particular problem. Okay. Let's keep it going here. Problem number 9, mowing lawns. So remember the work principle that we went over in the last section. The work principle has a formula that basically says this. It says, let A represent the time of person A to do one job, right? Same for B, except for B is the other person. Then this is the formula we use. 1 over A plus 1 over B equals 1 over T, where T is the total time that it takes to do the job. So for this one, we say, Bill can mow a 100 square foot lawn in 3 hours. And honestly, this is the first time I've ever actually considered the dimensions of this problem. A 100 square foot lawn, that's a 10 by 10 lawn. That's 10 feet by 10 feet. it takes Bill 3 hours to mow that lawn. Like that lawn has to have some very gnarly terrain, or Bill is just a terrible mower. And so is Kim, honestly. I mean, it takes her 2 hours. I mean, give me a break. A 10 by 10 lawn that should take you 10 minutes. Okay. I don't know why I'm complaining, because I made up the problem. So here we go. So, oh, and one more thing. I know I do say a 100 square foot lawn. I remember I specifically put that in there to mess with people, right? Because people are so tempted to want to put 100 square feet somewhere in this problem. But 100 square feet, it's just one job, right? I didn't have to put the square footage in there. It could be 2,000 square feet. This would still be the same exact problem. It would not change at all. The time that it takes to do one job is the important part. So, okay, we'll call Bill person A and Kim person B. So 1 over A, so 1 over Bill's time, which is 3 hours, plus 1 over Kim's time, which is 2 hours, is equal to 1 over the total time, T. So now I have a rational equation. All I need to do is multiply through by the LCD to clear all these fractions, and then I have a plain old equation, the kind that I love. Since all the denominators are prime, the LCD is just all those denominators multiplied together, which is 6t. So I'm going to multiply both sides of this by 6t. And after this, there should be no more fractions. Otherwise, I've got the wrong LCD. So I multiply in here, and I have 6t over 3. Multiply in here, and I have 6t over 2. That is equal to 6t over t. I'm going to go through and do some simplification. I'm going to switch to blue because why not? 6 over 3, that's equal to 2, so I have 2t. 6 over 2, that's equal to 3, so that gives me 3t. And then 6t over t, the t's will cancel, and I have just a plain old 6. Now, I just combine my like terms, which gives me 5t. And remember, this is one of those easy solutions because this is a degree 1. There's no degree 2 up here, right? It's not t squared, so this is an easy solution where we just isolate t. Now I divide both sides by 5. And I have t equals 6/5. And so what you would say on this one is let's see now, Bill and Kim working together can mow the lawn in 6/5 of an hour. So one thing to keep in mind when it comes to these work problems is just kind of like check your answer to see if it even makes sense, right? I got 6/5 hours. That was less than the total time that it took Bill or Kim to work on that lawn working alone, right? And so that kind of makes sense. If I would have got the number 15, that wouldn't have made a whole lot of sense, right? Because it takes Bill 3 hours to do it alone, Kim 2 hours to do it alone. Why the heck would it take them 15 hours to do it together? Unless the lawn is too small and they keep getting tangled up. That could be, but we're not considering that. All right, and so just make sure that your answer makes sense. If the answer doesn't make sense, chances are something went wrong. Okay, moving on. Similar triangles. So we assume these triangles are similar. Here, I need to actually fill these in a little bit. A, B, and C. There we go. That says these have the same angles, which means they're similar. Similar triangles are proportionate. So A over B is equal to C over D. All right, and the A and the B should be noted. The A and the B should come from different triangles, right? So if this A comes from the first triangle, the B should come from the second triangle, and they should be on the same side, sort of. So we have X over here on this leg over 574 on its corresponding leg is equal to 3 over its corresponding leg, 100. Okay, so now all I need to do is multiply both sides of this equation by 574. And that's going to give me x equals some decimal number, I think. Actually, that's not too bad. That gives me 17.22. So that is roughly what, not roughly, that is exactly what x must be. And you say, like, does that make sense? Well, it kind of does, right? And that's just because we look at the ratio on this triangle that we use sort of as our anchor. It's a pretty big ratio, right? That looks like 5.74 per 1. And so if you have 3, that would make sense that it's roughly, it's a little bit above 15, 5.74 per 1. So yeah, this answer makes some sense. We like this. If we were worried about it, we'd do the whole thing again. Okay. Now, here is a towboat problem. So, suppose there are 2 towboats, or tugs, which tow freight barges on the run from Seattle, Washington to Ketchikan, Alaska. The tug Jenny B makes the trip in 55.675 hours. The Banner makes the same trip in 111.35 hours. Due to its larger engine and more efficient hull design, the Jenny B has an average speed that is 6 miles per hour faster than that of the Banners. How fast is each tug traveling? All right, so this is a D equals ST problem. Distance equals speed times time. And so we have, like I went over in the last section, what I like to do with distance problems is to make a table. Across the top of that table, I write D, S, and T. And on the side of that table, I write either the difference in legs, the difference in people, in this case, it's the difference in the 2 tugboats. So Jenny B, and Banner. All right, the distance, they say they make the same trip. Notice that is actually underlined, the same trip, because that's really important to this problem. So I'm going to just leave the same trip as capital D, right? Same distance for both of them. The speed, it says the Jenny B has an average speed that is 6 miles per hour faster than that of the Banner. So if the Jenny is x, the Banner is x minus 6. The time, it gives us the exact time, 55.675 for the Jenny and 111.35 for the Banner. All right, so since our equation is D equals ST, and both of these STs, this one and this one, equal the same D, this one and this one, we can say x times, or we can say 55.675x, which is S times T for the Jenny, is equal to capital D, which is also equal to 111.35 times x minus 6, which is SD for the Banner. Now I just get rid of that middle D and set them both equal to each other. So I have 55.675x, and that is equal to 111.35x minus 6 times whatever that is, 6 times 111.35 equal to 668.1. Okay, so now, let's see now, I am going to add 668.1 to both sides. And then I'm going to subtract 55.675 from both sides. All right, and so that's going to give me 55.675. What do you know? X. Now I'm going to divide both sides by that number. And when I do that, I get x is equal to 668.1 divided by 55.675, which equals 12. So let's go back up here. So that means x was the speed of the Jenny B. So the Jenny was going 12 knots. The Banner was going 6. All right, so that would be the final answer to this word problem. So just remember, this one was set up the way it was because we had the same distance. I believe yesterday we had one that had the same time, right? And so that's another variation. If they have the same time, and then you have to set up your d over s equals t equation. One more variation is when you're dealing with two legs of the same distance. You know, that's kind of the other variation. So that's it. I believe that's my last problem. Yes, it is. So yeah, I hope that this went well for you. If any of these problems are still confusing, like, you know, please come see me in my office or come see Bethany on Monday, Wednesday, Fridays. I believe it's noon to 4:30. You know, we've got an exam on Tuesday. And so now is the time to get this stuff down and get it down so that you know it. So that's it. I hope this video is helpful.